And this is really isn't a tutorial, it's more just an overview of kind of what's new in HPC. When we do the registration, we ask for feedback on what you want to hear about or what you want to see, and some other people had suggested a few generic categories, so this kind of just became a mixed bag of things of what's new in high-performance computing. And some of the plenary talks from David Keyes and from Rick Stevens already gave you an idea of kind of what's coming up in kind of more of the DUE space and maybe from other sources. And I'll kind of give a general review where things are in HPC and kind of where we think, what we see coming, and maybe some of the things to think about in the next couple of years as you continue forth developing new codes or trying to keep your code running on new systems. Where do I go to look for what's going on in HPC? The 2 or 3 things that I look at mainly is, first of all, HPC Guru is quite good. He's pretty good at attending a lot of the conferences that I don't spend my time attending, so he gives you an update of what's going on. Glenn Lockwood, who works at NERSC, formerly I think at San Diego, he's quite good as well. He covers a broad spectrum. Right now he specializes a lot in I/O and data. But he has a good blog and a good Twitter account, keeps you up to date on any papers that are coming out that are really relevant, quite good. And Next Platform is good. It sometimes is too self-referential, but Timothy Morgan Prickett, who's one of the writers for Next Platform, is quite good in HPCD material, and usually has some good articles in there. So those are the primary things that I look at when not having access to other things from vendors, for example. It's true just about in anything that what's old is new again, especially in HPC. So some of the things that we see going on coming down the road is that Ethernet is now popular in HPC. There's a movement. It's Ethernet with a little extra oomph. Cray has something called Slingshot, which is coming out. Some of the newer systems that are going to be available for some of the DUE labs will be using Slingshot. So it's based on top of Ethernet, allows centers to mix hardware on a same network, which might have special Ethernet cards that can handle Slingshot while also supporting generic Ethernet cards as well at different speeds, but it makes it a little bit easier for centers to mix in different classes of components. On the I/O side of things, this was mentioned, I think, by Rick Stevens, or maybe or maybe Dan Stanzioni, that for file systems, we're seeing definitely a movement again away from POSIX I/O, strict POSIX I/O. That's slowly being relaxed more and more. Some of the semantics, for example, being strict locking is another one of those things that from time to time goes away. We see a lot of people trying to bring in the concepts from some of the data object store type technologies and mixing those two things together. So that seems to be gaining more and more traction. So seeing these really large Lustre file systems with strict POSIX support are starting to really maybe not be possible and scalable. And as it was mentioned by Dan, I/O tends to be one of the things that causes the most system-wide outages. And so trying to reduce that dependency on highly scalable, highly synchronous I/O would make systems more stable. And of course, just like if you look back over the years in HPC, there seems to be ebb and tides in new technologies. So again, we're seeing more new accelerators and we're seeing more new CPUs. So we'll dig into that. Okay, what does HPC look like in the States right now? So go back and look when Blue Waters was first deployed around 2012, 2013. The two big systems that were put out there, Titan and Blue Waters, they looked very similar. Titan was all XK, so one GPU and one CPU, and then Blue Waters, of course, was a mix of both. You can see quite a bit in the difference in the peak flop rates based on the number of GPUs. But that kind of put both DUE and NSF out there with the idea that maybe GPUs were the way to go. And some of the other centers started going after the many-core Xeon Phis as well. And we kind of know how Xeon Phi ended up as a technology that quickly dropped out of favor after many people tried to port their applications to it and found that it was often quite difficult to do. But they're still out there, and those systems are still available. And then we saw a kind of a tick-tock back to GPUs. So Summit and Sierra came out just last year into production with very heavy fat nodes with lots of GPUs on them. People are saying that perhaps that's not quite the way to go so heavy with those. Puts a large demand on the interconnect per node. So now you have compute nodes with multiple teraflop capability with a small amount of pipe coming out of there to keep those GPUs full. And one thing that Dan mentioned yesterday on Frontera is that they had to make a compromise on how they interconnected all their nodes, and they took a high speed, they had HDR for InfiniBand for their interconnect, but they put 2 nodes per HDR pipe, and so effectively having the bandwidth. So there's another example where centers have to make trade-offs and kind of puts their system in a certain functionality corner. And then recently we heard some really interesting announcements as part of the ECP program. So NERSC, Argonne, and ORNL have some new systems that are going to come online, hopefully in 2020 and 2021 or 2022. And you'll see it's quite interesting. First, no IBM. That was kind of interesting. Second, you start seeing a kind of mix of vendor mix match, right? So now we see AMD now with, again, NVIDIA GPUs. We see Intel now with an Intel GPU. So we all know Intel GPUs are in all our laptops and desktops, but now it's going to be a standalone accelerator. There's not a lot of information on that, but that's going to be out there. And then ORNL decided to rock the boat and kind of mix AMD CPU and AMD GPU. So at a point where it looked like we were just going to have one GPU and 2 CPUs, now we're seeing a rise again and more complexity. One thing I'd like to note is another system that came online, I think in March or April, down in a little town called Katy, Texas, outside of Houston. A oil and gas not provider, but a consulting company that works with a lot of the oil and gas industries, put down probably one of the largest commercially available HPC clusters out there. So they went, I guess, and bought up all the remaining Xeon Phi and put down a 125 petaflop system for supporting their oil and gas codes out there. So we've seen some other changes going on. So it's kind of interesting to see how industry's responding and providing it for their own niche computing. So they, DUG it stands for down under, so Australia, down underground geosolutions. And they have a system called DUG McCloud down there. So they put it in Texas, outside Houston, because apparently they found a very inexpensive data center to house it, the power was cheap. Changes to the landscape. Most of the time, acquisitions and mergers don't have such a big impact, but we know that the number of vendors is getting smaller, or at least the number of large-scale integrators has changed quite a bit. So many of you know that HPE recently acquired Cray, and HP, before it became HPE, has a long history of pulling in other companies and then those things slowly disappearing. So we're a little nervous. We hope Cray fits into HPE and maintains its presence in its current form. The one thing that I think that's interesting to note here that I highlight in black from the point of view for us and for you all who are running applications is Cray is probably one of the remaining compiler vendors that's fully open to support OpenMP for our accelerators. Okay, so Cray, as of about a year and a half ago, stopped support for OpenACC. So they stopped ACC support at 2.0. They didn't go to 2.5. And they've said that they're not going to go. They're going to support GPU technology using OpenMP. Okay, well that's interesting. So a few years ago, NVIDIA had purchased PGI. PGI was the primary developer of OpenACC, well, one of the main developers, implementers of OpenACC. So now we know we have 3 GPUs. We have an NVIDIA GPU, an AMD GPU, and now an Intel GPU. But there's not a common, at least simple compiler directive-based programming language to support all 3 of those. So that makes it a lot more complicated coming down the road. Another thing to note is Intel, a couple years ago, purchased an FPGA company, Altera. Haven't seen how that's going to you can buy products now. You can actually use OpenMP with Intel to drive these FPGAs now as well. So it's kind of interesting that you can do place and route and drive that via OpenMP. So that's kind of interesting. So well, these are changes. We don't know how they're going to pan out, but from the point of view of how we support you guys when we start getting new systems, or as you're out there looking at new systems, figuring out how you're going to run on them is getting, again, complicated. Many of you know that ARM is now a viable HPC solution. There's been a lot of work with the Thunder X2 system out there. Cavium was the company that was initially pushing that out. They recently got bought last year by a company called Marvel. And then Fujitsu has been, last year announced that their post-K machine is going to be based on ARM as well, what they call the A64FX. That looks like a really interesting processor. As I said, Intel recently announced that they're going to be pushing their XEZ, I'm not sure how to pronounce it, GPU. Google has made available their tensor processor unit right now through the cloud. And I'll note later in the talk that there's an interesting little standalone device you can get for $145 that lets you get one little tensor processor unit that you can run for inference. But I'm guessing at some point people are going to provide generic SDKs so you can use it for something else. And then one of the companies that Rick Stevens mentioned that they're looking at as part of this testbed system that they're going to develop up at Argonne for letting the public evaluate different processors from machine learning is this company called Tachyon. They have a processor that's called the Prodigy CPU. It's not actually physically available yet. They're taping it out anytime. It's one of those companies that you hope isn't just vaporware. But it's really interesting. It has many of the same features and benefits of the ARM processor. It's not ARM-based. It's like ARM. It's not x86 compatible. But it looks really interesting. It has a lot of nice features, so we'll try to highlight some of that. So the best way for us to simply evaluate what the potential is, at least for most of the processors out there, is just to look at the peak feeds and speeds. And then Dan gave a really nice discussion of how peak speeds and feeds can be misleading, and certainly fraction of peak. So the information that's here, I'll give a clock rate that's kind of provided by the vendor, or in some cases, our best guess of what we think the actual processor clock rate is during normal operations, and the peak flop rate would take that into account as well in the memory bandwidth. So we have, just for reference, the Blue Waters processor, the AMD Interlagos, and then at the same time, for those of you who were running the Intel Sandy Bridge, was kind of the comparable. And I put that there because at the time, AMD, this is one of the few times where AMD processors and Intel processors provided almost nearly identical performance for many workloads. So they had the same peak flop rate and the same peak memory bandwidth. So the byte per flops were relatively decent at 0.3. But many people noted that there was a difference in performance when they would run on systems such as, I think, Yellowstone, or maybe at NERSC as well, Edison. And in fact, what was happening is that the Intel, one reason why Intel chips are more expensive is they put more effort into their caches. So Intel caches tend to be faster. They provide higher bandwidths, and that's sometimes where we see a difference, and we'll show in the paper in a little bit that is actually easily seen. Currently out there right now is Intel Skylake and now Intel Cascade Lake. So those are fairly powerful processors as well. They're a little expensive. The ARM Thunder X2 that I just discussed being rising in popularity has an interesting trade-off. So Thunder X2 has a little bit lower compute power, but it has a higher memory bandwidth ratio. So you actually have a better bytes per flop ratio. So bytes per flop is how much data you can use or need to reuse for the number of flops that you want to do. So the higher that number, the less floating point operations you need to do per byte read to get good performance. And so it's doing quite well. It's also not nearly as expensive as an Intel processor, for example. So depending on your code characteristics, this is actually a viable solution. Cascade Lake is what's on Frontera. AMD Rome is interesting. That's going to be one of the processors for some of the new systems coming out at Oak Ridge. And also a new system in Germany that was announced accidentally a few months ago. And that's also nice. You notice it has a very good byte per flop ratio. It's not great. It's going the wrong direction, as Rick Stevens noted back on Tuesday. But it's trying to get back up there. So this is where we jump back to some of the new chips that are not available yet. So Fujitsu has an ARM component which is projected to have a really good byte per flop ratio of almost 0.75. So you can see that they're putting a lot of emphasis on the memory bandwidth. So they're moving that memory wall that was talked about the other day, where it makes it difficult if you have codes that require a lot of memory streaming. So it's an interesting balance, interesting trade-off. And then there's Tachyons out there. Not too sure what the clock rate is, but it's going to provide supposedly 8 teraflops per CPU. I mean, that's huge compared to anyone else. If it's going to really be out and viable in the next couple months by next year, wow, I mean, that's going to be a real game changer for a lot of applications. And the memory bandwidth is not great to keep up with that floating point rate, so some applications won't find that benefit. So we know those things are coming out, so we like to highlight things, and this came out last week. AMD had announced that their Rome processor was out, and they were highlighting it at Comdex. And the CEO said, hey, look, we can run AMD on this new AMD processor and compare it to what's coming out from Intel, the Cascade Lake, and it's 2 times faster than Cascade Lake. And, you know, everyone's like, wow, that's pretty impressive. Maybe the benchmark wasn't run quite right. We had Jim and a few other people from an AMD group had some comments about the way the benchmark was run. Intel says, hey, that doesn't sound right. There's no way we're 2 times slower. So they went ahead and made sure they had the right compilation flags available and was able to show that they got roughly the same performance as Rome. Okay, that's nice. You know, Cascade Lake gets the same performance as AMD's new Rome processor. But if you were to go look at the price differential, let's say you wanted to run nothing but an AMD, you can get almost, at least twice as many Rome chips for the same price as Cascade Lake. So, the price per flop or price per performance is interesting. So benchmarking, you got to be careful what the vendors say. We had done some work with a group from University of Bristol and participated at least in the single node evaluation of the ThunderX2 ARM processor a while ago, and these are some results from 2 different papers, one from 2018 at the Cray User Group meeting and one from 2019 on the Cray User Group meeting as well, showing various single node performance speed up improvements compared to some of the older Intel chips compared to the ThunderX2. And the interesting thing is, and it's what you kind of see from the peak flop rate, the peak speeds and feeds, is that the applications that were memory bandwidth limited did better on the ARM processor. The ones that were more CPU bound, because the caches are faster on the Intel processor, did better on the Intel processor. They did some scaling work on their system. They have a Cray XC50 with the Aries interconnect, and so scalability should be quite good for most applications. And they were able to run these on various XC30s, XC40s, XC50s that all had the same interconnect, but different processors, and were able to show that, depending on the dependencies of the application, as they strong scaled these applications out, things that started to fit into cache, Intel processor-based systems saw bigger speedups than the ones from based on ARM64 processors, on ThunderX2 processors, sorry. Anyway, so these are things that you'd really want to look at when looking at your code if you don't have access to these new systems. Vendor benchmarks, okay, not so good to look at. Look at some better academic studies. The interesting thing, and I thought this was kind of brave, if you go look for the CUG 2019 paper from Simon, they actually did a price performance model as well and showed that there's a significant benefit by performance per dollar for the ThunderX2 for many of the applications. For most of you in the audience, you're not buying the processor, so it's not a concern to you, but it's a concern to us when we're trying to provide a system. So to summarize kind of the things that were observed by the papers there, AMD and ARM typically are slower with cache, so if you are doing any real strong scaling, working on Intel systems might be better. If you're memory bandwidth limited, the new ARM processors that have 8 memory channels do a little bit better. Intel's coming up with Rome has 8 memory channels as well. Intel will have an 8 memory channel system once Ice Lake comes out, which is supposedly sometime next year. And vectorization is important. As you know, many of you have tried Xeon Phi with the 512 byte-wide vector units, or even on the newer Cascade Lake chips. Wider is better for operations, but it comes at a clock speed cost. And so Dan highlighted that you can get anywhere up to a 20% slowdown in clock speed by using these wider vector units. So depending on how vectorized you are, it might be better to try AVX2 compared to AVX512, depending on the technology. And ARM, when they come out with their newer version, whoever, like Fujitsu, for example, they'll have a different vector engine that supports 512. On the GPU side of things, NVIDIA is kind of really happy with their Voltas right now, the V100s, but we know that an Ampere-based system is supposed to be coming out. There was some hint that this would happen at the most recent GDK conference that NVIDIA has, but that didn't happen. So I don't know what to put for Ampere performance, but we know it'll be better than Volta. So here's what the Volta numbers are for double precision, single precision, and half precision. So many of you are doing machine learning, half precision is important, or if you're doing mixed precision computation, which is becoming more and more popular, more and more algorithms are being written to handle mixed precision, you can kind of see what the numbers are, and then what the memory bandwidth is for 1 Volta. So we know AMD's back in the game for HPC. What does its GPU look like? Well, the peak speeds and feeds are close to what you would see for a Volta. The biggest difference is half precision performance. So the AMD Radeon doesn't have these tensor processor units like the Voltas do. So that's the biggest difference for half precision. But note that they have higher memory bandwidth. So depending on what your application looks like, an AMD Radeon Instinct GPU might perform quite well. And I'm going to guess the price differential between a Volta and an AMD Radeon might be, I don't know, a factor of 10 possibly. It's really hard to say. And then we know the Intel GPU is out there, but we don't really have much information on that. So back to the things that people in my group work a lot on is the software aspect. How do we support these different GPUs in your codes? So like I said, we have NVIDIA, AMD, Intel. There's no common accelerator base. CUDA works great on NVIDIA. Doesn't work well on Radeon or this new Intel GPU. So how are we going to do these? And also with the vector engines as well, with different vectorization technologies now with ARM and possibly this Tachyon. It's getting complicated to support. There was a nice presentation by Forrest Glines, one of the graduate fellows, who showed about using some of these frameworks from some of the national labs, so COCOS, for example, for people doing C++, which apparently is going to become part of the C++ standard for enabling codes coding to a generic API, so to speak, so they can generate CPU code or GPU code without any difficulties. So that's interesting. And once it becomes a standard, you're a little more comfortable recommending it to someone. If it's still just a product from a national lab, you're a little worried about how long it'll be around and whether it'll be supportable. And then, of course, the vendors are going to try to come up with things that allow you to use their technologies. Intel has their one API, which I don't know much about. There isn't much information on it. But AMD has been promoting their ROCm and their HIP stuff for a while, which allows you to use their CPUs, their APUs, their GPUs, or even taking some CUDA code, run it through the HIP, and get some code that will run on the AMD GPU as well. So with that complexity, there's no, I mean, if you ask me what do you recommend, how to program for any of these new CPUs coming out, or even the GPUs, I really, at the moment, can't give you a good recommendation. So one of the things that we do typically is look at compiler performance. So this is going to be a big issue going forward when we're going to have 3 or 4 different CPU vendors. And we already saw, even with Python, that it can be messy with loops. Compilers even have a big issue. So we have a recent paper from CUG in 2019 where we've evaluated how well compilers do on Blue Waters. Long established system, nothing should be changed much lately. And the new Cray XC systems on Skylake, which are also kind of production systems. And you can see a wide variation in performance capability of the compilers. So Cray, Intel, PGI, and GNU are all the ones that are supported on almost every Cray platform. And wow, your mileage varies a lot. GNU is the most commonly used compiler on Blue Waters. It may not be the most used by node hour. So if there's an application out there that's compiled, it may not be the one using most of the time node hour wise, but GNU compiler is the most dominantly used one. It might not be giving you the best performance, so that's a big issue. We hope to extend this to also include ARM now, and then whatever we get access to down the road. So we're trying to show that it's important to really look at the compilers to see how your how well you're doing. And for portability, you pick GNU, it'll be everywhere, but performance-wise, you may not do well. New technologies, quantum computing. I don't really have much to say. I know I was hoping someone else like David Keyes would talk a bit more about quantum computing, and he said, well, we'll see what comes out of it. Some of the national labs have invested a lot of money into it. NSF is putting a lot of money into it now. At NCSA, we haven't really done much with it. University of Illinois and the Illinois system is trying to get up to speed and start becoming more of a leader in quantum computing, at least understanding what's going on. I remember back when I went to SC in Reno, back in 2007, there was a company off in this separate room, in the disruptive technologies room at SC called D-Wave, and everyone was like, ooh, quantum computing, what's that? Back then they had something with like, I don't know, 24 qubits or 16 qubits, and now they're up to several thousands because they have a slightly different definition for what qubits are. Some of the other technologies that are coming out, different implementations. I really don't know what to say. I'm not familiar with it in any sense of a traditional HPC application. We know that they do well for things like encryption, decryption, things like that, encoding things, code breaking possibly. For quantum information, for sending large amounts of data securely, that's probably what they're really good for right now. But for actually using quantum mechanics, quantum computing to solve a quantum system, I don't know how well that's going to work, or solving binary black hole collisions with PDEs. It's uncertain, but it's definitely going to, it's there. So something to understand. And a lot of the companies like Microsoft and Google and Amazon or whatever, they're providing these cloud computing resources with APIs and SDKs that you can actually do it right now, and they have emulators and simulators to try things out, small algorithms. So, hey, things might work. Hard to say. I'm getting close to the end here. One thing, Galen, that many of you know, he likes to play around with things like little processor kits and try things out. And so he noted the other day, like 2 weeks ago or 3 weeks ago, that Google said they made their TPU available. So you can't go and buy a tensor processor unit from Google. You can get access to a cloud, but they're willing to sell you this little standalone developer's board with one TPU, one little unit in there for $156. You can download it. It'll run Linux with Python, and it'll let you run a version of things called TensorFlow Lite, which is only for inference. But the fact that they're exposing it out there means that someone's going to figure out a way to rip out any kind of technology control that this little TPU has, and pretty soon I'm sure someone's going to find a way to run generic code, not just TensorFlow Lite on this little thing. And now we have a little development board for learning how to use a Google TPU. Maybe Google at some point will sell it as something that we can provide as a HPC resource. So who knows? I mean, it does MATVEX quite well, so there's something there. Current trends, whoops, somehow this is not the most up-to-date slide. Current trends in I/O, I just want to finish out real quick on what's going on there. I don't have a lot of content there, mainly because I kind of realized I was going to run out of time, and Jim was on vacation for a lot, so I didn't get a chance to talk to him. Blue Waters, when it came out, originally we had this concept with a lot of other centers of this tiered storage kind of concept, where you have maybe really fast, but not as much storage that's close to the compute node. And as the farther you get away, then you get down to slower but bigger. So things on the system with non-volatile memory, solid-state drives, to spinning disk, to tape, for example. So you would get these really deep hierarchies in tiers. And then also other things with I/O accelerators like burst buffers, which allow you to write data close by on the network and then move that off to spinning disk as well. They're rather complicated. They make your workflows really messy. But they're out there. NERSC has spent a lot of time doing that, Argonne as well. But for example, Frontera, Dan Tack took the point of view, well, we don't need to do that. We're just going to provide some concurrent file system at the same level. Some flash-based stuff, SSDs, and some spinning disk as well. So that's great. So that's kind of what we're seeing is this tiered stuff was looking interesting, but it's too complicated to manage. So I stole this slide from DDN, who's one of the developers of a lot of the storage that people in HPC use, and what they're finding is that, well, it's great, we have all these different layers, makes it difficult to make them in a tiered level. Maybe we need to flatten things out based on what your application does and provide more, different layers at the same level, and then have stuff at the back end. So these are things that tend to be not always on the front burner for when you're writing a proposal. Storage often comes in second. But we've really been working hard. I think Blue Waters was one of the first systems in which that wasn't the case. I mean, it was the first system to have a terabyte a second bandwidth for reads and writes to a large-scale file system. So we know it's important. So hopefully any future system that we manage to put out will have a really complementary file system. But so that's kind of where things are going. The POSIX-related aspect, which makes it difficult for these large-scale file systems to function at high performance, is probably one of the reasons why at TAC they have 3 separate file systems besides the reliability aspect or the metadata load aspect. And then there are non-POSIX file systems out, or non-POSIX storage solutions out there that are becoming more and more popular. And once there are APIs that make it easy for standard HPC codes to write to these blob-based type file storage devices, then you'll see that coming up more and more. But at the moment, things are kind of in this mixed mode where they're trying to figure out where to go. So I have the URL for that if you want to read what DDN thinks is going to be going on in the next 5 years or so. I don't know about a decade. That seems kind of long, but maybe in the next 5 years.